Hello everyone, today I'm going to be solving this paper with you. So it is the May-June 2023 paper, and this is for Pure Maths 2, Zone 2-2. Let's just jump right into it. The first question we have is a trigonometry question. We've got sec squared theta plus 5 tan squared theta is equal to 9 plus 17 sec theta. And they're saying solve the equation. So you can see I've copied my trigonometry part of my MF19 just into this document for making it easy, but I really encourage you to print out an MF19 and have it next to you as you are solving these because it will help you to get used to the paper. Alright, so when we're looking at solving trig equations, there's different strategies that we can use. In this case, I can see we've got a sec squared theta and a tan squared theta. And if I look at my MF19, I know that there is a relationship between tan squared and sec squared. And then I also have been given a sec theta. So one of my strategies is to create a quadratic. If I can get a quadratic or something that looks like a quadratic equation, I can solve it using my quadratic formula or factorizing. And that's going to break it down into smaller pieces that I will be able to solve in my calculator. So I can see that I'm aiming for a quadratic in this case. And because my middle term is sec theta, that one is not easy to change. So I'm going to change my tan squared theta into sec squared. So let's just take a look. We've got 1 plus tan squared theta is equal to sec squared theta. So I usually just make the term that I want to get rid of is my tan squared theta. So I'm making that the subject of the formula. Okay, so if I rewrite my equation, I've got sec squared theta plus 5, and then I'm going to replace this with my identity, sec squared theta minus 1, and that is equal to 9 plus 17 sec theta. Okay, so I just did that on the side here for you, but make sure that you're comfortable transforming this into only sec squared and sec because we're going to aim for a quadratic. So if I simplify this, theta minus 5, okay, then I can add my like terms together. So here I have my like terms, and then I've also got a constant and a constant, and then my sec theta is on its own. So it's going to be 6 sec squared theta. I'm going to get all my terms to one side. And then minus 5 minus 9 is minus 14 is equal to 0. Okay, you can try and factorize this. Okay, that seems to work. So minus 3 plus 4. So you might have different ways of factorizing. I'm just doing that on the side. You can also use the quadratic formula to solve this. So what we have here is 2 sec theta minus 7 and 3 sec theta plus 2 is equal to 0. So sec theta is 7 over 2. Sec theta is minus 2 over 3. Right, so now we've broken this down into something smaller, so we can solve each of these. However, we don't have sec on our calculator, so we need to change it to cos. What you do need to remember, it's not given on your MF19, but you need to remember that sine theta is 1 over cosec theta. Cos theta is 1 over sec theta, and let's say rather tan theta is 1 over cot theta. So that on the side plus all of these identities is what you need to know for trig. All right, so what we're going to do is we're going to flip this over. So cos, we're going to turn it into a cos theta, and that means that we flip our fraction upside down. 3 over minus 2. Okay, if we take a look, we've now got two answers. This one is going to have no solutions. The reason for that is if I draw out my cos graph, we're going to look where does the graph intersect at negative 1.5. So that's actually down here, negative 1.5. And my cos graph only goes down to negative 1. So there's not going to be any solutions for that specific graph. If we look at this one over here, we've got cos theta is equal to 2/7. And we are looking in the interval of 0 to 360. So I can expect to get 2 answers for this equation. Also, take note, working in degrees. Working in degrees. So if I just get my theta is going to be my inverse cos of 2/7. And just make sure your calculator is in the right mode. That gives me 73.4 degrees. And this is my reference angle. That's this angle over here, 73.4. And I also know that theta is negative 73.4 degrees. This is if I look at symmetry. Okay. But this negative angle is not what we're wanting because it's outside of our domain. So I have to just add 360 to that to get the next answer in my domain. And I should have 2 answers. And Cambridge likes to have any degrees must be given to 1 decimal place. So I've got my 2 answers there. They seem reasonable. If I look at what I expect my answers to be, they look about right. So I'm just going to then say theta is 73.4 degrees or theta is 286.6 degrees. And that is my final answer. Okay, let's move right into the next question. So here we have a log. Well, this question comes from the chapter of logs and exponentials. And what we're doing here is we're transforming a log to linear form. Okay, so the first thing that you need to do when you're transforming it to linear form is you just need to take note of what's on the x and y axis. So here we've got an x, so that's normal, but on the y axis we've got a ln y, not a y. So if I was to write a straight line formula, I normally have y is equal to mx plus c, but in this case I need to transform my graph to be a ln y is equal to mx plus c. All right, and what you also need to note is these values over here, that's an x value and that's a ln y value. That's x and that's ln y. So that's really important. First, take a look at what's on your axes. Okay, so it says the variables x and y satisfy this equation. So in these questions, they generally give you the equation that is satisfied. A minus bx. A and b are constants. Okay, the graph of ln y against x is a straight line and it's passing through those 2 points as shown in the diagram. Find the values of a and b to 3 significant figures. All right, so we always start with the graph that they give us, our exponential graph, and we're just going to be using ln and log rules to transform this equation into this format here. Ln y is equal to mx plus c. All right, so first of all, what I'm going to do is I'm going to ln both sides. And you need to know your log and ln laws really well here. Now, this is made up of an a and let's just call it a b term, so 2 terms. So I'm going to split them using my log laws. So if they're multiplied, I then add them. Okay, and generally these steps are the same. They look a bit different for each question, but the general idea is the same. I'm going to bring down my exponents. I must remember to keep everything kind of in a bracket there. Ln e, in this case, ln e is actually 1, so it's going to cancel out, but I'm just going to use another line to show that, or let me just cross it out there. And what I'm going to do, I'm going to keep my a minus bx. Okay, I'm going to just keep my x there. I just want one x in the equation because I'm trying to make this look like this, a ln y and an x. So as you can see, I've already got my ln y, and I'm just going to move this term, a minus b x plus ln a. All right, so what you can see here is our a minus b is our gradient. It's going to be the gradient term. And then our ln a is our c value. So now I've got my ln y is equal to mx plus c. So that's the first part of doing this. And now there's different strategies to solve this. What I'm going to do is just use simultaneous equations. I'm going to plug in my values. What you could also do is calculate your gradient. The gradient, and that equate that to a minus b. I'm just going to do simultaneous equations for now. All right, so we're going to take our first point, and here you need to make sure that you plug in the right thing into your equation. So my ln y value, I'm going to start with my point down here. So my ln y is 3.6 is equal to a minus b, and then my x value is 0.4. That's ln a. All right. And so here we have a 0.4. I can see this is going to start to become a bit interesting. Okay, I'm actually going to just leave it like that for now. I'm going to write down my next equation. So that's going to be 14.1 is equal to a minus b. And then my x value is 2.9 plus ln a. All right, so I've got two equations here. I've got two unknowns, my a and my b, so I should be able to solve for them if I use simultaneous equations. Okay, just trying to think what is going to be the easiest way to do this. If I make a the subject of the formula, I've got an a here and a ln a here, so that could be a bit complicated. If I make b the subject of the formula, that can work, but it's also quite complicated. So while I'm looking at this, I'm just going to, rather than go into my gradient, I'm just going to write up another formula as well. So my gradient is my change in y over my change in x. I think this is just going to make things a little bit easier for me. So I'm going to say 14.1 minus, and in this case it's my ln y. Okay, so it's whatever's on your straight line. And then 2.9 minus 0.4. Okay, so if I look at this, I've got 14.1 minus 3.6 over 2.9 minus 0.4. And that gives me 21 over 5, or an answer of 4.2. Okay, I think that's actually going to make life quite a bit more simple, because this is now equal to my a minus b value, because that is my gradient if I look at my formulas. So now I'm just going to rewrite this formula. 3.6 is equal to, instead of a minus b, I'm going to say 4.2 times 0.4 plus ln a. Okay, that immediately makes it easier. There's different ways to solve these. I think you can practice each of them. Okay, 1.92 is equal to ln a. If you have one ln on one side, you can raise each side to e, and then those inverses cancel out. 1, 2, and they ask us to give a and b to correct to three significant figures. So a is then equal to 6.82. That's three significant figures. And a minus b so if we plug that in, we've got a b value of 2.62. Okay, and those are our a and b values. So in this case, because I had a and a ln a, it didn't look like the easiest thing in the world to make A the subject of the formula, and B also just looked like a lot of work. So it's totally possible you could just use those two equations and do simultaneous equations. But I mean, you could even make A minus B the subject of the formula. But you've always got this other tool in your pocket that your gradient is then equal to, and it's whatever, whenever you manipulate the formula to look like your y is equal to mx plus c, it's equal to that. So in this case, it was equal to A minus B. So that's just helpful to know that extra little tip there. And in this case, we did use it, but you don't always need to use it. Right, and that was our second question done. So they asked for A and B to 3 significant figures. I always like to just check that I've answered the question that they asked me for. If I have time in my exam, I like to go back and I like to check my answers in whatever way possible, normally in a different way to the way that I calculated it. But anyway, let's keep going. Question number 3. All right, the diagram shows part of a curve. Okay, so we've got some sort of reciprocal function here. The shaded area is bounded by the curve, and the lines x is equal to 6 and y is equal to 2. Find the exact area of the shaded region, giving your answer in a specific format involving lins. A and B are integers. All right, so now we are in the topic of integration. We're looking at the area under a curve. In this case, we're actually going to calculate the area of the rectangle and then subtract the area under the curve. That is going to give us the area of the shaded region. All right, and we're just going to use our integration, and then it looks like we're also going to be going into logs and lins. Let's get going. So our area of the shaded region is going to be our rectangle. So I'm going to say my 6 times 2. So that's just length times breadth. 6 times 2, I'm going to take that full area, and then I'm going to subtract the integral. Now I'm wanting to go from the curve. Whenever you do an integral, it works out from the curve to the x-axis, and you have to use your boundaries on that axis. So I'm going to be going between 0 and 6. This is my curve, and I'm going to be integrating in terms of x. All right, so that should give me the area of the shaded region. Right, so no tricks to that. Okay, I am actually going to integrate immediately. I don't need to prepare my integral. So what I see is that this is a reciprocal function. If you go onto your MF19, let's just quickly dive in there. You can see, make sure you're under the correct topic, so that's differentiation, integration. If I integrate 1 over x, it's going to give me ln x. So this is the parent type of function that we're going to be using, except you can see that we have a composite function here. So instead of just 1 over x, we've got a 6 and we've got a 2x plus 3. Okay, so I'm going to, in this case, my 6 is just my coefficient. I'm going to keep my 6, and then I'm going to integrate the entire fraction at the bottom. And we can do this because the this denominator is linear, so you are allowed to do it. But we need to just remember our chain rule, or our reverse chain rule, where I need to divide by the coefficient of x. Right, so I divide by the coefficient of x, and then I'm going between 0 and 6. I need to remember I am subtracting this entire term. Right, so I'm just going to make notes for myself, and I'm going to use a big bracket to do this. Right, now we're just diving into a definite integral. First of all, my 6 and my 2 become a 3. My 2 times 6 is 3 minus 2 times 0 plus 3. Okay, please note that the second term is not falling away completely. Sometimes when you plug in a 0, you expect it to fall away. Okay, so that becomes 12, 13, 14, 15. Ln of 15. I don't really need to mod it because it's already a positive number. Minus 3 ln 3. Okay, just note that they asked us to give our answer in this format, A minus ln B. Right, so we want to keep our lns. We don't want to plug this into our calculator. Okay, I'm going to use my ln or log laws. So I'm going to take my exponents up. Now I'm going to combine these fractions, ln 15, and then I'm going to divide by 3 to the power of 3 because my lns were subtracted. And at the end, if I plug this into my calculator, I get ln of 125. And that is my final answer. So they wanted it to be A minus ln B, where A and B are integers. Okay, so we also needed to go from, we didn't want to leave B as a fraction at all. Okay. And that is question 3 done. So integration and a little bit of ln and log laws. All right, let's dive right into question 4. So the diagram shows the graph of y is equal to 3 minus e to the power of minus a half x. And they say on the diagram, sketch the graph of, and then they give us a mod function. Okay, and show that that equation, so the curve and the mod, has exactly 2 real roots. Okay, so we need to expect these things to be meeting each other twice. That will give us 2 real roots. Okay, so the easiest way that I find to draw these mods is I first find where is my x-axis now, and I do that by equating this to 0. So x is going to be 4 over 5, and if we take a look, that is about 0.8. Okay, so if that's 1, I guess our x-axis is going to be somewhere along here. I should have done this a bit more specifically. I just drew lines now, but I actually want to look. The gradient of my line is 5, so it's quite a steep line. If I want to look at my y-axis, so it's always good just to label important points. My y-axis is where x is going to be 0. So it's going to be 5 times 0 minus 4. So y is going to be 4. Right, so let's make this quite steep, I think. Okay, and that must cross at 4. So it's going to look something like that. I'm just taking a look. I want to try and compare it to this graph actually. If I make my x naught, e to the power of naught is 1. So this one crosses at 3. So actually, I'm going to make my graph steeper. I want my graph to cross at 4. Okay, so that was worth doing, just to show that you know it's a very steep graph. Okay, obviously I'm doing this on an iPad now. You might want to have thought about all of that before drawing it on your paper. So that crosses at 4. Just show where it crosses on your x and y axes. Okay. And then what we can do here, they also say show that it has exactly 2 roots. So we can just, I don't know, highlight it and just say our x1 and our x2 is exactly 2 roots. Okay. Right, now it is given that the 2 roots of that are denoted by alpha and beta, where alpha is less than beta. Okay, so if I was to relabel this correctly, that would be alpha and that would be beta. Okay, let's just get a few things here. Show by calculation that alpha lies between 0.36 and 0.37. Okay, so which topic are we now in? Can you see that we're now going to be heading quickly into numerical analysis? This is a really interesting question. They did get us to draw the graph so that we can see exactly what's going on here. So can you see whenever you have a mod function, you've got basically two arms. That's your positive gradient going in that direction, and in this case, you've got the negative gradient going in the other direction. So if I look at where does my curve and my mod function, which arm does the curve intersect with the mod function to give me alpha? And you see that it's the left arm with the negative gradient. So before I start, what I'm going to be doing is I'm only going to be using my negative arm of my mod. So I've changed the sign of both terms in the mod. I'm going to be using the negative. And now we need to show that alpha lies between those two. So I'm going to get all my terms to one side. Let's just say 5x minus e plus 4 minus 4. So that could look like any, you could take it to either side and put it in any order, so long as you've got your signs right. And I'm going to plug in a 0.36. And my answer is minus 0.035. So I get a negative answer. And what I am expecting here is to have a sign change. So that is all that I'm actually wanting to show, is that I get a sign change when I plug in these different values. Okay, so I'm just going a little bit back on my calculator and typing in 0.37, and here I get an answer of 0.018, let's just say 9. Okay, and so therefore I can conclude sign change, and therefore alpha lies between 0.36 and 0.37. I should have just started writing probably from over here. Okay. Now, they say use the iterative formula, and they've given us an iterative formula. That's really nice of them. To find the corrective 4 significant figures. Give the result of each iteration to 6 significant figures. Okay, so we're just going to be doing our iterative formula now. We can literally use the formula that they've given us. Okay, and I'm going to say my first value, so my n1, sorry, not my n, my x1 is equal to 0.36. So what am I doing? I'm now going to plug 0.36 into this value over here. So, and then just see what you get on your calculator. Times 0.36. Okay, you could have started with 0.36 or 0.37, doesn't matter. And now we're giving 2, 3, 2, 9, 5. Okay. Okay, so now 6 significant figures for each of these. Okay, so that's what my answer is if I plug that in. And now I can just go back to my calculator, and instead of retyping the decimals each time, just type the significant, type in the answer button. Okay, so my next value is 29203, and then I can just now say equals 29517 equals 29534 equals 29535. Let's just see, they want us to give an answer to 4 significant figures, so I think we can conclude that x is 1.295. And that is my final answer. Okay, so you just do it until eventually the first 4 significant figures aren't really changing, and then you know you've got your answer. Right, let's jump right into question 5. So here we have the diagram, shows this curve. Okay, immediately when I look at this, I can see product rule. Okay, we've got a quadratic and an exponential multiplied by each other. The curve crosses the x-axis at the points A and B, and it has a maximum point at C. Find the exact gradient of the curve at B. Okay, so we want the gradient of the curve at B, so it's going to look something like this. Well, actually, it's probably a little bit like that. Okay, we want to know the gradient of the curve at B. So we're probably going to need to first find where is B, and after that, what's the gradient. So gradient, we want to know dy dx at the point x is equal to B. But let's just first find where is our B. Okay, in order to find B, B is an intercept, so it intercepts the x-axis, and so we know that is where y is equal to 0. So I'm going to just have my graph. Okay, because I've got two factors, I know that each of them can be equal to 0. Okay, an exponential graph never has any value equal to 0, so that's not applicable, or no solutions coming from there. And here we can factorize this into a -4 and -1. Okay, so x is going to be equal to 4 or x is equal to 1. Okay, we've got two places where our graph crosses the x-axis, so just through logic, we know that that's 1, and then b is equal to 4. Okay, so now we know where we are looking for this answer. Let's keep going. So find the gradient. So now I'm just going to rewrite my formula. X squared minus 5x is 4. We need to use our product rule. So you need to find UV on your MF19. So I'm going to go to my MF19. I don't actually use the MF19 to do this, but let me just show you. Under differentiation, you're going to use this rule over here. So you have a product, U times V, and so you can differentiate U and differentiate V, and then just kind of paste the pieces together as per the product rule. So I do a little bit something different. It is the product rule, exactly the same thing, but I just do it by remembering that what you need to do is derive the first term and then leave the second term. So I'm first going to derive my E. E stays E, but because there's it's a composite function, you also have to get the derivative of the inside function. So derive E, and then leave, so derive the first term, leave the second one. Well, derive the first, what is that, like factor, leave the second one, and then you leave the first one, and you derive the second one. Okay, so that's just 2x minus 5. That's simple differentiation. Okay, so that is my product rule. If you go and use your U and your V, you should come up with the same thing. I don't need to really simplify this, but just for the sake of something a little bit neater. Two x minus 5. Okay, I'm going to now plug in my 4. Probably could have done that earlier, but anyway. So 4 squared minus 5 times 4 plus 4. 5, okay. Probably encourage you to find the exact gradient. Okay, so you can't just plug this into your calculator and get a decimal value. You need to simplify this thing slowly. So half e to the minus 2. And then obviously you can use your calculator. Not that you should need to, but sometimes Okay, this is 16 minus 20 plus 4, so that becomes 0. Interesting. This is also minus 2, and then here we've got 8. And then times 3, so our final answer is going to be 3 over e squared. Or you could also say 3 to the 3e to the negative 2. And that is what you would call an exact gradient. Okay, that is part A. Let's take a look at part B. Find the exact coordinates of C. All right, so we need to keep it at an exact value. And what is C? C is a stationary point. So even though it's a maximum, it doesn't really matter. It's just, well, I guess there would be 2 stationary points in this graph. So we're not looking for the one between 1 and 4. We're looking for the one that's greater than 4. But that is where your dy dx is equal to 0. Okay, so we've already got our gradient formula. I'm going to go back to this part here. And I'm going to say minus a half e x Okay, so the trick is, how do you solve such a thing? Okay, so this gradient, I've written it a bit funny now, but anyway, that gradient is now equal to 0. And yeah, not so straightforward to simplify, but what I'm going to do, so if you can get factors, if you can get this thing into 2 factors, you can make each factor equal 0. And that's generally a very good place to start. So I'm going to start there. I can see, so I've got 2 terms here, and each term has an e to the negative half x. Okay, so I'm going to take out that term, and I'm left with minus a half, and then my whole bracket, and my other bracket. Okay, so now I've got 2 brackets. I've got one over, well, I've got 2 factors, one over there and one over there. So I know that each one of these is equal to 0. Or this whole thing is equal to 0. And now I can, this is kind of like a quadratic, so I'm actually going to just divide through by a half. That's in my way. So x squared minus 5x plus 4 plus 2x minus 5 is equal to 0. Well, I can't just divide through by half because it's not connected to all the terms. Oh my goodness. Okay. Minus a half x squared. Minus and minus becomes a plus. Minus 2 plus 2x minus 5 is equal to 0. Okay. If I multiply everything by 2 now, that will get rid of it. I'm going to do a negative 2. So that becomes x squared minus 5x plus 4x minus plus. Okay, right. You got to make sure you get that right, otherwise it's just losing marks for silly things. Okay, we really need to be careful every time we do this. So x minus 7, x minus 2. Okay, so I've got 2 points where I have a stationary point. In this case, it's either 7 or 2. Does that make sense? Yes, absolutely, because we expect there to be a stationary point somewhere between here. And then our 7 is obviously going to be where C is. All right, so they say find the exact coordinates of C. So they want the x and the y coordinate. Therefore, x is equal to 7. And so y is going to be, we're literally just going to plug 7 into our formula. Not into our derivative, we've got to plug it into our original graph, and that's this one over here. I'm just going to copy it and paste it. Obviously, you can rewrite it. Okay. Seven, and then 7 squared minus 5 times 7 is 4. And that is going to give us e to the power of negative 7 over 2. And then we have 7 squared 18. e to the power of minus 7 over 2. So our coordinates of C are 7 and 18e negative 7 over 2. Okay, super strange answers, but go back and check your work, and if you've done everything correctly, you can confidently just leave it like that. That is the correct answer. All right, moving on to question 6. Okay, so we've got 2 questions left. Here we have another trigonometry question. So I've also copied a little bit of a snapshot from our MF19. We need to show that. All right, so this is immediately an identity. We're going to show that the one side is equal to the other side. Right. What can I see here? I can see compound angles. So I'm going to need to be using my compound angle formulas. Right, so you need to make sure that you're familiar with that. I'm not going to necessarily go through the detail of how to do that. I'm just going to go. What you need to be careful of is that if you have a coefficient like this, you've got your 4, then your entire compound angle needs to be in a big bracket. Okay, so I've got my sine theta cos pi 3 cos theta sine pi 3. Okay, so that's my expansion of my sine, and that is multiplied by cos. Well, actually, let's just put this whole thing in brackets. Multiplied by cos theta cos pi 3, and then cos always goes to the opposite sign. Okay, please note you're also working in radians, so now our calculator needs to be set to radians. These are special angles, so you don't even need a calculator to work them out. I don't really want to think too much, so I'm just going to use mine. 3 half. Insert. And then sine pi of 3 is going to be root 3 over 2. All right, so now we are getting this a bit more simple. I like to simplify if I have cos and sine values that are actually, like, if I can simplify them, I generally do. Otherwise, you end up not having like terms. So this is really helpful just to simplify them so that you can get more like terms. But in this case, we had to multiply now. 4 times sine times cos, all compound angles. So we've got a bit more work to do. In this case, we're going to multiply each term by each one. Might get a little bit messy, but just make sure that you keep going. Do exactly what you need to do with your distributive laws now. I'm going to keep my 4 outside in the meantime. Okay, so a quarter sine theta cos theta plus we have 4 sine squared theta plus root 3 over 4. Can you already see something? Cos squared theta. I've got a sine squared and cos squared. 3 over 4 sine theta cos theta. Okay, so I'm just using my distributive law because I really don't actually know what else to do. So you just keep going. These things often get messier before they get prettier, so don't be afraid of going for it. Okay, now I'm actually just going to simplify. I can see that I've got some like terms here, so I'm going to simplify before I multiply my 4 in. So I've got a quarter of sine theta cos theta and 3/4. So actually, 1/4 plus 3/4 just leaves me with 1. Okay, and here I'm going to take out 3/4 and I'm left with the sine squared theta. Okay, so I can immediately see the reason I did that is because I want my sine squared and my cos squared to cancel out using my identity. Alright, so if I could probably do this in one go. And then my sine squared, this becomes 1. And my 4's cancel out, and so I'm left with that. Alright, we're getting a little bit closer to what we want. We've got my √3, and can you see they want me to have a double angle here? And I know that this is my double angle. Side, okay, because my double angle sine 2 theta is equal to 2 sine theta cos theta. Alright, and we've just proven that. So you might want to rewrite that just exactly how they want it, but basically we've proved it. So don't be afraid to get a bit messy before we get a bit neat. And what I can say is you can't always see the end goal. I can't see the end goal when I start, but you just have to start somewhere. So don't not start because you don't know the end goal. Okay, just start. Alright, and then they say find the exact value, and then they give me something. So with these, you always want to see how is this related. This is very interesting what they gave me here because okay, they give me 4 sine, they give me this whole thing, and then they give me cos and that whole thing. So I'm just trying to see how does this relate to my part A. And if I look at part A, I've been given 4, because I can see these angles are not the same. So something is funny. Okay, so 4 sine theta plus pi over 3, and then cos theta minus pi over 3. Okay, so what is related here? Could I say, I just want to see, if I say theta plus pi over 3 is equal to 17 pi over 24, what's my theta going to be equal to? So 17 pi over 24 minus pi over 3. My theta is 3 pi over 8. Okay, so I just did a comparison here. Okay, and I just want to see, does it hold? So cos 3 pi over 8 minus pi over 3, does that give me 1 over 24? It does. Okay, right. So you just have to kind of figure out the puzzle piece here, okay? I just saw, the first thing that I saw was that these are different numbers. And when I looked up at my term here, I've got a something plus and a something minus. So, you know, if theta was a value, does it connect? And yes, it does. So I know that my theta is 3 pi over 8. Right. Okay, so you might need to do that somewhere on the sideline just to get the connection between the two. Theta is 3 pi over 8. So I basically know that that is equal to 2 sine 2. Okay, I'm just using my identity above. I still don't know exactly where it's going, so 3 over 8 times 2 is 3 pi over 4. So 3. Okay, and if I get my sine of that value, sine of 3 pi 4, that gives me root 2 over 2. And this simplifies to root 2 plus root 3. And they do want it to be in exact form, and I can't really simplify that any further. So that is my final answer. Okay, really interesting question. I'd be interested to know if you are able to do it any other way. Maybe give it a try. Might not have been your first go-to, what I did, but yeah, that's my thought process as I'm doing this. Okay, then we're jumping right into part C. So this says integrate. It's a definite integral, and this also looks something like above. So we've got 4 sine and then 2x plus pi over 3 and 2x minus pi over 3. So in this case, we know that theta is equal to 2x. Okay, so you always want to look for the similarities, and how does this connect to, how does it connect to our original identity? And then we're also going to just use our identity. It's most likely going to be needed. Okay, so in this case, it seems much easier to integrate our identity than this complicated thing over here. But we need to remember that theta is 2x. Okay, and I'm just going to put this in a big bracket, and I'm integrating now in terms of x. Okay. Just to make it 4x plus root 3. Okay, one thing you need to note is that we are able to integrate sine, cos, or sec squared in this paper, so long as whatever is inside is a linear function. So in this case, it is a linear function, so we can just directly integrate. Always remember your notation though. So I'm going to keep my coefficient. When I integrate sine, so you might just want to double check on your MF19. Make sure you go to integration, not differentiation. If you integrate sine, it becomes minus cos. That becomes minus cos. Then you keep the inside, but we have to divide by the coefficient of x. Okay, and then root 3 just gets an x. It's a definite integral, so we're going to plug in our boundary. Okay, I am just taking extra steps here. Okay, so 4 pi divided by 8 is basically pi over 2. Minus cos of 0 is not 0. Okay, so always just double check. Your terms don't always fall away. Okay, cos of pi over 2 is 0. Whenever I do this, I just think of my graph. So my graph goes down at pi over 2, it's 0. Okay, so we've got root 3 pi over 8 minus cos of 0, this becomes 1. So minus and a minus becomes plus half. And then the root 3 falls away. So we end up with pi root 3 over 8 plus a half. And that is the correct answer. That's the exact value of that integral. Okay, so always watch out whenever you've got these trig things in part A, part B, part C, make sure that you make the connection between part A, part B, and part C. Otherwise, it's going to be very difficult to try and integrate something like this. Okay, we don't actually have the tools for that in Pure Math 2, so take note. Right, we're going to jump right into our last question, and we can immediately see this is parametric equations. Those are quite fun. All right, and that falls under the topic of differentiation, where they give you a third parameter. In this case, we have a third parameter of t. Right, so they give you x in terms of t, they give you y in terms of t. A is a constant. it is given that the point P on the curve, at the point P on the curve, the gradient is 1. So we know dy dx at P is 1. Show that the value of t at P satisfies that equation. Okay, so we basically need to get our gradient formula and make it equal to 1. That's the first place I would start. The tip that they gave us is that at point P, the gradient is 1. Okay, so let's just start there. Once again, this is one of these questions that I don't know the answer to yet. I'm just going with what I've been given. Okay, here we need to use the quotient rule. So make sure that you know on your MF19 where the quotient rule is and how to use it. I don't use the MF19, I'm just going to do it this way. So derive the first term, derive the numerator, which is just 2, keep the denominator, minus, and then keep the numerator, and derive the denominator, which is just 1, and then square the bottom, square the denominator. Okay, so that is our gradient formula. Okay, we know we are looking for where the gradient is equal to 1. So, oh wait, no, this is not our gradient formula, this is just our dx. Let me just simplify this to make it a bit simpler. Minus 2t minus 3 over t plus 2 squared. And that just becomes 1. Okay. Alright, so we haven't even done half the work yet. I'm way jumping what I need to be doing here. dy dt. Let's first figure out what y is. Be a good start. That is t squared plus at plus 1. Okay, so dy dt is 2t plus a. So that's quite straightforward. So if I then get dy over dx, that's going to be my dy over dt times dt over dx. Right, so that's also on your MF19, and you just need to know whenever you have a parametric equation, you need to use that formula, because that links the 3 variables together. Okay, so our dy over dx is going to be 2t plus a, and then I'm going to flip this upside down, because I'm looking for dt over dx, not dx over dt. You just have to flip the whole thing. Okay, so we've got 2t plus a times t plus 2 squared. And now that's our dy dx. And we know that we want it to be equal to 1. Okay, my equation does not look like the top equation. Not yet. So I've got a t3 up here, t to the power of 3, and then something t squared, and then a t. So I'm just going to start multiplying out, because I can see I'm going to get a here. This is going to give me a t squared, and then when I multiply by t, it's going to give me a t to the power of 3. So the only thing that I know to do is start multiplying out. So I'm just going to jump over to the left here. I'm going to say qt plus a. So maybe as you're doing these papers, the more papers you do, the more practice you can get as to where you're going to write. 4. Okay, so I've got to multiply this out. Squared. Okay. 4a minus 1. Right, and what they've done is they've put a t squared, t, and then they've grouped everything. So I'm just going to see what happens if I do that. Okay, so my t squared, I've got an 8 plus an a. And then my t values, I've got an 8 plus a 4a. Okay, and then if I just zoom out a little bit and take a look, is it the same? So I have got a t cubed and a t cubed, and then an 8 plus a t squared, 8 plus 4a, and then a 4a minus 1. So that looks correct. I have proven what they've asked me to prove. Okay, so can you see, once again, it's not so straightforward as to what are they asking for, but they've given me enough clues. I know what topic I'm in, I know what formula I have, so I can just start. My original answer did not look like what they wanted, so then I just do the next thing that I know, which is multiplying out, and yeah, eventually simplifying. So don't be afraid to just keep going. Okay, all right, this is interesting. It is given that t1 is a factor. Okay, so we are now into polynomials. If t1 is a factor, that means if I plug in t equals minus 1, my answer should be 0 because it's a factor. Okay, let's try it. Find the value of a. So I'm going to say let p of x Just out of interest, let's look at the next question. Hence, show that p is the only point on the curve where the gradient is 1. Okay, cool. I was just wondering what they were going to ask me there. Okay, so if you're not sure, what you normally do is you make your factor equal to 0, and then that's the root that you need to plug in, minus 1. 2 times minus 1 to the power of 3. Oh dear, plus 4a minus 1. Okay, I'm taking a bit of space here. So minus 2. Okay, so all of that should be equal to 0. So let's just simplify a bit. So plus 8 minus 8 minus 4a. So I'm left with a is equal to, that's not a, 1, 2, 3. A is equal to 3. My final answer. And then lastly, hence. So use be above something or other. Show that P is the only point on the curve at which the gradient is 1. Okay, so we need to see that where dy dx at the point P, and P satisfies that equation, and that equation, let's just write it down, is now going to be into d3 plus 3 plus 8, that's an 11t squared, plus 3 times 4 is 12, 20t plus 12 minus 1 is 11. So that's my polynomial. Hence show that P is the only point on the curve at which the gradient is 1. Okay, so that is my polynomial that I came out with. But I just want to see my dy over dx is equal to 2t plus a and t plus 2 squared. Alright, and then when that whole thing is multiplied out, okay, so we already know basically when I multiply this whole thing out, it gives me my polynomial. We already know that this polynomial has one answer, and that is where t is equal to -1, so t plus 1 is a factor. Okay, so if I divide this, what do I have left? And that, whatever I have left, should have no roots, if that makes sense, because otherwise you're going to have more answers. So let's just see what we have left. So we've got to do some polynomial division here. So 2t squared okay, so divide, multiply, subtract 11 to 9, bring down becomes 9t. Oh, sorry, I forgot to bring down. Okay, so now we've got 9t squared plus 9t. And bring down an 11. Okay, becomes plus 11. So 11t plus 11. So then there's no remainder. So now I've got t plus 1 and 2t squared plus 9t plus 11. Right, so I just basically want to show that this has no roots. I think the easiest way to do that is to show my discriminant is less than 0. So that's going to be 9 squared minus 4 times 2 times 11. And what does that give us? So 9 squared minus 4 minus 2. Oh, minus 4 times 2 times 11. And that gives us negative 7. Therefore, no solutions. Oh, I'm running out of space here. The only t plus, no, only t is equal to -1 is a root. Okay, and so therefore only point where the gradient is equal to 1 or dy dx is equal to 1. Okay, so I didn't do that very well with space, but that is our final answer. And there you have it, your Pure Math 2 May, June 2023 paper 2-2. I hope that this has been helpful.